Back in 1931, a single research paper dropped, and it sent this massive shockwave through the worlds of math and philosophy. It basically suggested that the entire search for absolute certainty, for a perfect, unbreakable system of logic, well, it was doomed from the very beginning. This is the story of that incredible idea.
So let's just start with the huge question that Kurt Gödel's work really forces us to confront. Is there a fundamental, built-in limit to what mathematics can actually prove?
To really get why Gödel's discovery was such a bombshell, we have to travel back in time to the early 20th century. It was this era of incredible optimism. Mathematicians genuinely believed they were right on the verge of creating a perfect, all-powerful logical system that could handle all of mathematics.
Now, these were the two holy grails they were chasing. A system had to be complete, which just means that if a statement is true, you can prove it's true, and it had to be consistent, which means you can't prove something ridiculous like that 1 equals 2. The absolute dream was to build one single grand system that had both of these properties.
And the champion of this grand ambition was the brilliant mathematician David Hilbert. His goal was, nothing less than to create a set of rules that could basically mechanize all of math, getting rid of all paradoxes and uncertainty for good.
But there was a bit of a ghost in the machine. It was a problem that philosophers had been wrestling with for centuries, the strange, loopy nature of self-reference. Just think about the classic liar's paradox. This statement is false. Okay, so is that sentence true or false? Well, if it's true, then what it says must be correct, which means it's false. But if it's false, well then it's a true statement. You see? It's just an endless, unresolvable loop. A total logical black hole.
And this is where our main character enters the scene. A quiet, absolutely brilliant logician named Kurt Gödel. He looked at this ancient philosophical puzzle and asked this groundbreaking question. What if you could translate the liar's paradox into the pure, formal language of mathematics itself?
So to pull this off, he needed a way to make math talk about itself. And the method he invented was so clever, so ingenious, it honestly feels like a magic trick. He called it arithmetization, but today we mostly know it as Gödel numbering. This was the absolute core of his genius. He figured out that he could assign a unique number to every single piece of a formal system.
And this just lays out the idea perfectly. First, every little symbol, like a plus sign, an equal sign, or a variable, gets its own number. Then, by combining those numbers in a really smart way, entire formulas get their own unique number. And then, a whole chain of formulas, an entire proof, could also be represented by one single, probably massive, but unique number. So here's a really simplified example from his paper. The symbol for 0 might be the number 1. The symbol for naught could be 5. A parentheses could be 11. All of a sudden, logical statements could be encoded as plain old numbers.
And this is the crucial point, right here. A statement like, "This formula is a valid proof," was no longer just some abstract idea about symbols. It became a statement about the properties of numbers, something that could be analyzed right inside the mathematical system itself. So, armed with this incredible new tool, Gödel was finally ready to set his logical trap. He was about to build a sentence that the system could never prove, but also could never disprove. So he meticulously constructed this very specific, self-referential mathematical formula. And just to keep things simple for us, we're going to call it statement G.
And what did statement G say once you decoded it from its Gödel number? In the pure language of arithmetic, it said, "This statement is not provable within this system." He did it. He had created a mathematical version of the liar's paradox.
So this leads us to the big, inescapable question. Is statement G provable? Let's really walk through the implications of this together, because this is where it gets wild. And this is the checkmate. Let's break it down. First, let's just imagine the system can prove statement G. Okay, but G says it's not provable. So if the system proves it, it is proven a lie. That means the whole system is inconsistent. It's broken. So, what's the other option? What if the system can't prove G? Well, in that case, statement G is actually true, because it claims it can't be proven, and guess what? It can't be. But that means your system is incomplete. You've just found a true statement that the system is totally powerless to prove. Either way you go, Hilbert's dream of a perfect system is completely shattered.
The fallout from this discovery was, and honestly still is, just immense. It basically placed a permanent question mark right at the heart of mathematical certainty. This is what we now call Gödel's first incompleteness theorem.
It basically says that any formal system of math, as long as it's powerful enough to do basic arithmetic and it's consistent, will always contain true statements that it simply cannot prove. There will always be truths just beyond its reach.
And as if that wasn't mind-bending enough, he delivered a second, maybe even more devastating blow. The second incompleteness theorem says that no consistent system like this can ever prove its own consistency. So, that whole quest to build a system that could pull itself up by its own bootstraps and declare itself perfect, yeah, that was now officially impossible.
You know, Gödel himself thought a lot about what this all meant. He wondered, does this mean that mathematics is just too big, too vast for our minds to ever fully grasp? Or does it suggest that the human mind, our ability to step outside the system and see that statement G is true, is something more than just a complicated machine?
And that leaves us with one last, kinda haunting thought. If even the pure, precise, perfect language of mathematics has these built-in, inescapable limits, what does that say about the far more messy, ambiguous, and self-referential systems we use every single day? Our own languages and our own minds.